Sound travels at a particular speed. I gave you that speed earlier. Let's see, I don't know, it's a few hundred meters per, 340 meters per second. You don't need to know that number, obviously, but it has a particular speed that it travels at in the medium. That 340 meters per second is the speed of sound in air. But that speed will travel differently. Sound will travel differently at different speeds depending on the medium. The speed depends on the elasticity of the medium. A more elastic medium has a higher speed. The elasticity of a medium, I don't think I spelled that right. Elasticity of a medium describes how quickly it returns to its equilibrium position when displaced. So you might think of a rubber band as having a high elasticity, but a rubber band is pretty flexible, right? That you can stretch it, and it doesn't have a quick return to its equilibrium position than, say, I don't know, a solid material. Um, so a spring with a high spring constant is very elastic. So we talked about earlier, if you have those springs in your car that hold your car up versus, say, a rubber band, that the one of these with the higher spring constant is the springs in your car because it requires a very large force to displace it from its equilibrium position. So it has a high spring constant. That might be sort of different from what you might think of an elastic material, but a material that has a higher elasticity will return to its equilibrium position much more quickly. That also means that it requires a very large force to displace it from its equilibrium position. So of these, the solids, liquids, and gases, which is the most elastic? Well, if I displace a gas from its equilibrium position, it may not even go back to that position, or if it does, it takes a while. And likewise for a liquid, that I can move a liquid around more easily. So uh, given that progression, then I'll say that a solid is the most elastic because, a solid has this very rigid structure. And I think if I can come in here and take, say, this atom and move it off to the side, then the other atoms are going to push it back really quickly. It has a very high spring constant, if we want to think of it in terms of a spring constant, though this isn't really a spring. Though I will say that in physics, the spring constant and the idea of the simple spring is something that we use often to describe how atoms interact with one another. Anyway, so the solid is a very elastic material. I know that's different than what you might think, but it's elastic in the sense that the atoms, when displaced, will return very quickly to their equilibrium position. So steel, for example, is one of the most elastic materials. The speeds then of sound you'll see are quite different. In water, the speed of sound is about 1,500 meters per second. Air was what, 340 meters per second? I don't have it for steel in meters per second, but I have it in miles per hour. So in water, it's 3,400 miles per hour. You don't need to know these numbers. I'm just sort of giving them to you for reference. In air, that's 760 miles per hour. So as we think, liquid is more elastic than a gas, so the speed of sound in water is higher than that for air. But in steel, it's even that a much greater speed of 11,400 miles per hour. So the elasticity for these materials we'll find are increasing as I move from air to water to steel. And those, we would find too that if I was moving from water vapor to liquid water to ice, I would find a similar progression. And so typically the elasticity increases as I move from gas to liquid to solid. In a gas, you can change the medium to alter the speed of sound. Small molecules move more quickly, So sound travels faster. We saw this in a video earlier, I think it was in the Khan Academy video, that if I have, a little bitty molecule like this, it's just going to be more nimble and able to move more quickly. And so sound will be able to displace it more quickly and it will travel faster. However, if I have a molecule, I don't know, that's bigger, then it's not going to move as quickly. You can think of it as having a greater inertia, thinking back to Newton's first law, but it has a bigger mass, it's just a bigger molecule, so it's not going to move as quickly. Also, if you raise the temperature of a gas, the speed will also increase. It's like those molecules are already moving around more quickly anyway because they have a higher temperature, and so that will cause the speed of sound to increase as well. Breaking the sound barrier. The book talks about this a bit, and I'll show you a video. This was first done by Chuck Yeager. Or Yeager, maybe? I'm not sure. In 1947. Later, this was done by a land vehicle. I'll try to find the video. Last time I looked, it had been removed by a land vehicle car. It's like a jet-powered car. In 1997. Hopefully you've experienced a plane or some other vehicle breaking the sound barrier. If you have, you will have heard a sonic boom. And this is very similar to the wake of a boat. Certainly you've experienced the wake of a boat. When you have a wake of a boat, the boat travels at a speed that is faster than the velocity of the water, or the waves in the water. The waves. So the waves, it's like they can't, I'm putting this in quotes here, but it's like they can't get out of the way. And so they add up to produce the wake that's seen on the shore. So if I think about my boat traveling with a speed that's bigger than the speed of the wave, right? This boat is giving off waves, but this one is slow. And so this one, which is coming more quickly than the wave in front of it can catch up, they're going to add up. And when that adds up, it causes a larger wave. So I'll show you another video actually from a Frozen Planet, where if I have two waves like this, and I add them together, it creates a wave that looks like this, that has twice the amplitude. This is called the phenomena of interference. Your book, I don't think it talks about interference. No, we don't get into interference, but I do want you to understand interference. This is called constructive interference. And on the other hand, I have destructive interference. So destructive interference looks like this, where I have a peak lining up with a trough and a trough lining up with a peak. And when I add those two waves together, I get nothing at all. So a similar thing happens. This constructive interference happens in the wake of a plane, that I have these waves that are catching up and lining up with one another so that they produce constructive interference. There are also visible effects due to pressure variations in the sonic boom, and I can't. It's hard to describe. I'll share you a video that shows some of those visible effects.